Okay, so last example before we try the tutorial. What we're going to do this time is basically the same thing as last time. So you're going to find a resultant force and couple at O. So you're going to find the resultant of all these forces and what would be the appropriate couple. Where's it going to be going? It's probably going to be going down somewhere. Hard to say. Just imagining drawing them all nose to tail to get an idea of where that force would want to go. So it's probably going to be down here somewhere maybe. It's going to be your resultant force, Fr. And we're also going to have a couple, probably going to be going in that direction, Mr. So we're going to take all those forces and figure out what's the equivalent resultant force and resultant couple at O that would produce the same effect as all of these forces. And then for part B, we're going to find if we were to get rid of that couple, where would we have to put this on the x-axis, which is interesting. X-axis is not there. Where would we have to put that to get the same result, so the same effects at the origin O? Okay, so the first thing I'll do, I've redrawn the diagram. Probably just delete that for now. Redrawn the diagram. I've drawn on all my x and y components. The first thing I'm going to do is to find the x component of that resultant, which is just going to be the sum of the x components of the other forces. And then the y component of that resultant, which is going to be the sum of the y components of all these forces. Just spotting that there's a few things I need to fix here. Calling that x, but it's really y. And this one's x. So we'll work through all that, and then I'll meet you on the other side of the fast forward. So we've got our x and y components of the resultant. And so if our x is 5.598, if our y is minus 6.5, so just copied that diagram and drawn these onto it. And so our resultant vector, so our resultant force, runs like this. So that's the resultant force. What I'm going to do now is I'm just going to quickly check that by drawing a scale. So I've drawn this to scale, and I'm going to draw these force vectors onto scale as well, just to make sure. So just draw them nose to tail from that point O, and just check they end up at the same place, just to make sure I've got the right answer here. So it looks like we're on the right track. And so now what we'll do is just calculate the magnitude of that resultant vector and the angle to the x-axis. So got all those answers, and that looks correct. I'm just going to underline, what have I checked? Underline, well, you can see we've checked the vector itself. So that's been checked, this has been checked, because those are correct, everything leading up to that must be correct. So that's that. We're still not done though, so if we, that's the resultant of the vectors in terms of the force, it's the resultant force. But we also have to find the resultant moment now. Okay, so we combined all the forces, we've got the resultant force, we still need to find the moment. To do that, we just need to think about each of these components and what's their lever arm to the origin. So we're doing the moments, the resultant force and moment about the point 0 or O, about the point O. So what I'll do now is I'll go through and do all that. I'll find all the vectors. Let's just do one of them, I guess. And so say we start off with F1y, so its line of action is straight up through here. So it's got a line of action like so. Actually, it hasn't been drawn very well. And so the lever arm for that force is the shortest distance to the point we're thinking about, which is the origin in this case. And so that there is going to be d1. So I'll find all the others, and then I'll calculate all the moments, add them up, being careful about the direction, clockwise, anti-clockwise, clockwise, negative, anti-clockwise, positive. It's D1. And then I'll come back again. So that's us done part A. And so we found the resultant force and the resultant moment or couple. I'll probably just draw them on a clean diagram and write down the answer, and then we'll move on to part B. So I've tidied up the diagram just to show the answer. So we found a resultant force of 8.56 kilonewtons at an angle of 49.26 below the positive x-axis, and there's a moment at O of 2.46 kilonewton meters. And rather than write out a long description of that, just said the resultant force and moment at O is as shown in the diagram. Okay, so quick summary of what we did. So we were asked to find the resultant force and couple at O for this scenario. So what did we have to do? Well, the first thing we did was to try and find the resultant force, and it wouldn't matter which point you were asked to calculate it around. The resultant force is just the sum of the x and y components of the individual forces. So you sum all the x components, sum all the y components, and that'll give you the x and y components of the resultant, just the same as we've been doing previously. So we went through, found all the x and y components, added them together, and that gave us the x and y components of the resultant. So frx added up all the x components, fry added up all the y components, and from those we could calculate the angle and the magnitude of the resultant vector. And that was us essentially finished with the force. But as we're realizing now, we have to be careful not just to think of the force, but also we need to think about the moment about this point O. So then we've gone through. We've done it via components in this case, so just figured out what the lever arm was for each component and then multiplied force times lever arm to get the moment of each component. We could have done it alternatively, we could have traced these lines back and tried to use trigonometry to find the lever arm to the original forces rather than their components, but we'd already calculated the components, so it made sense to do it this way and add all of those up. So you're adding up, you don't just add up x components, you add up the x and y component moments. So add all those up and you get the moment about the point O. And then just to show that, we just drawn a diagram. The next part won't take us quite so long. What they want us to do this time is figure out, well, how can we get rid of this couple or this moment and just apply a force? And so we just want to apply this resultant force and not have to apply this moment. So the way you do that is you create a lever arm between this force and the origin, that point O. That's why I've left on the x and y components for just now. So we're on to part B. Now, let me think about how I can do this. Let me see if I can move this. So what's going to happen as we move this? So we're eventually going to get rid of this couple. So I'll just get, let me just copy it so I'm not messing up my answer for this question. So let's copy this. And so what we're trying to do is to eliminate that couple. And so that's going to be gone. And the way we're going to do that is we're going to move the point of application or the line of action of this force. So this resultant force. So we're going to move this along somewhere. So we're just going to move this along. See if I can do it. So it's asked us for the position on the x-axis. So we'll think about moving it in the x direction, so in this direction. So we're going to move that along. So the point of application is changed so that we now get a lever arm between the origin and the resultant force. and we're going to use that, we're going to make sure that that matches this moment that we had up here. How do we do that? Well, we want to make sure we've got the right lever arm. Now this one, there's a bit of a shortcut we can take. So this X component of this force, that's why I kept it there, it has 0 moment. So this X force, because its line of action passes through the origin, through that point O. So the only thing that's going to create the moment is this Y component. So therefore, if we can get the Y component times lever arm is equal to 2.46 kilonewton meters, we'll be on the right track. So let's try that. So let's say this, the sum of the moments is equal to what did we call it, MRX? I don't know why I'm doing it, so that's the resultant, plus MRY. But MRX, so the moment due to the X component of the resultant is just 0 because the line of action is through there. So therefore, MRY must be equal to 2.46 kilonewton meters. Let's just keep the, no, it was, yeah, it should be, keep it as 2.46. Let me just double check what the accurate value of that was. 2.459, yes, so it's 2.460, so it's 2.46. Just checking, because you want to keep, maybe you want to keep the 4 significant figures until we get to an answer. So it's going to be, I don't know why I'm writing that in just at the moment. Oh yeah, no, that's right, it's 2.46, so it's 2.46 kilonewton meters. Now MRY is just the Y component of that force times, so we'll just write it properly, so it's FRY times DRY. So the DRY is just the lever arm to the Y component. What colour do I want to do this in? And that's essentially what we're figuring out. We want to know where this sits on the Y-axis. So DRY is going to be equal to 2.46. Now we know that that FRY is 6.5 kilonewtons. So therefore we know 6.5 times DRY is equal to 2.46. So DRY is equal to 2.46 divided by 6.5, which equals 0.4 or something, is it? Something like that, I think. 2.46 divided by 6.5, 0.378. Yep, 0.378. That's our final answer. So 0.378, and I think all our distances were in meters, weren't they? Yes. So meters. Okay, so see how that works. We could have done it other ways. We could have looked at trying to find the lever arm to the main force, but in this case we'd already figured out the X and Y components, and we noticed that that X component has no moment associated with it because its line of action goes through the origin, therefore it's got no lever arm. So the only thing that's given you a moment is the Y component, and therefore we know that the Y component times its lever arm must be equal to the couple we had up here, this 2.46, and therefore we've managed to set up a little equation and figure that out and calculate that distance dry, and that was the answer to the question for B. B said find the magnitude of the force resultant without a couple and a position of its line of action on the x-axis. So we're just answering the question now, so I'll just write that out and that'll be us done.